As computer science students, you are training to build, manage, and secure the digital infrastructure that runs the modern world. Today's digital landscape is a massive, interconnected mesh, but this total connectivity creates a paradox. As our systems become highly capable and continuously linked, they become inherently more vulnerable to attack. Early computing took place on large, expensive, and isolated mainframes. These machines were used strictly for scientific and military calculations, cut off from outside networks. Communication technologies evolved independently. Simple point-to-point systems like the telegraph gradually developed into complex global data networks. The personal computer merged these two tracks. Computing power became accessible to the individual, pushing active data nodes out to the edges of the network. Modern wireless technologies accelerated this shift. We transitioned to networks capable of continuous, high-bandwidth data exchange across the globe at any given moment. This total reliance on interconnectivity eliminated the effectiveness of physical security perimeters. When every device can talk to every other device, the entire system absorbs the risk of its weakest link. Cybersecurity is a critical engineering discipline. It is essential to protecting digital assets, ensuring system reliability, and maintaining user trust in every system you build. Historically, security meant protecting physical hardware. You kept the machine safe using locked doors, thick walls, and security guards. Once systems connected, the threat model shifted. Attackers didn't need to steal the physical machine. They could simply intercept the data in transit. This required an entirely new set of modern cybersecurity practices. We can map out the fundamental attributes to secure interconnected data using an engineering canvas. Placing a single data node at the top, we support it with an architectural foundation. The first structural block is confidentiality, ensuring sensitive information is restricted to authorized individuals. We achieve this through encryption techniques, scrambling personal and financial data during transmission so that anyone intercepting it sees only useless noise. Next is integrity. Data must remain accurate and unaltered. Cryptographic hash functions scan packets, confirming original states and rejecting modifications. The third block is availability. This guarantees systems and services remain accessible whenever required. Cyber attacks like denial of service or DOS are engineered specifically to break this attribute by overwhelming servers with fake traffic until they crash. Together, we have confidentiality, combined with data integrity and system availability. These form the CIA triad. This is the absolute minimum architectural requirement for any secure digital environment. The CIA triad works well for closed systems, but in modern, multi-user environments where trust cannot be assumed, these three attributes are insufficient on their own. We have to expand our canvas to include a fourth axiom, authentication. This is the strict cryptographic verification of a user's identity before the system grants them access. Verifying a user's identity doesn't solve every vulnerability. Architects must mathematically prove exactly what that user did inside. This brings us to the fifth axiom, non-repudiation. Creating an immutable secure log file ensures users cannot deny their actions once a transaction executes. These 5 attributes form a complete logical model. Any complex cyber threat, regardless of its sophistication, can be deconstructed into a failure of one or more of these foundational axioms. With our model built, we need to stress test these axioms against today's hyperscaled technologies. We will start with cloud computing. Remote hosting provides organizations with flexibility and scalability, processing data on vast server farms rather than local hard drives. This architecture introduces a concentrated risk. By centralizing millions of users' data into single locations, we create high-value targets for attackers. When cloud environments have weak security controls or unpatched vulnerabilities, the result is a massive data breach. In the context of our model, this represents a failure in confidentiality and integrity. Let's look at the opposite end of the spectrum, the distributed edge of the network, driven by the rapid expansion of IoT devices. IoT connects millions of everyday devices to the internet. The danger is that these devices often lack adequate built-in security mechanisms. We see this frequently when smart home cameras or home automation systems are compromised by outside attackers. These compromises usually stem from inadequate default configurations. When an external node forces a connection to a camera, it represents a failure in authentication that allows unauthorized access. Both the scalability of the cloud and the ubiquity of IoT multiply the attack surface. In these environments, a single Axiom failure can cascade into a systemic, network-wide breach. We also have to account for artificial intelligence, which acts as a powerful, dual-edged sword in modern cybersecurity. Machine learning algorithms can enhance our threat detection and response times. However, attackers are simultaneously using those same algorithms to develop sophisticated, targeted attacks at scale. A primary example is AI-driven phishing. Attackers use large language models to generate convincing, personalized messages designed to deceive users into handing over confidential information. Phishing doesn't break the encryption, it bypasses it. By mimicking trusted entities, AI phishing exploits human failures in authentication, leading directly to a loss of confidentiality. The compounding effect of these breaches has forced a shift in societal expectations, resulting in a growing global emphasis on data privacy and ethical data usage. Social media platforms have faced intense criticism for mishandling user data, resulting in privacy violations and public fallout. In response, legal regulations and strict scrutiny are being introduced to mandate confidentiality and integrity by law when technical architectures fail. Technology alone cannot solve the security problem. Addressing human-related risks and enforcing data privacy are intrinsic components of a complete security architecture. If we pull back, we can see the full engineering canvas we've constructed, unifying decades of technological evolution. The digital world will continue to evolve, bringing significant opportunities alongside complex, systemic risks. The core logic remains constant. Every modern threat, whether it's a DOS attack, an AI phishing scheme, or malware, represents a mechanical breakdown in one of these 5 core security axioms. Mastering these historical and security principles is the absolute prerequisite for your professional career. As emerging technologies introduce new vulnerabilities, you must continuously develop both deep technical knowledge and a broad awareness of security concepts. Your career as a computer scientist centers on architecting resilient systems that can withstand the unseen threats of tomorrow.